guys, welcome back. All right, so last week we were talking about the series circuit, and this went really well for you guys. I'm really impressed with how easily you got a hold of this idea. If we want to pull stored chemical energy out of a battery, transform it into electrical energy along a wire or a circuit path in order to run different objects along the way. You did really well with this idea. So let's just take a very quick moment to refresh our memory here. A series circuit, and this is the most simple type of circuit that we have because there is only one path for current to flow. So if you look at these two images that are on screen here, they both represent the exact same thing. We begin with our battery, which is our stored form of chemical energy. And as we connect that battery to the wire, we create that potential difference, which means that the wire, the conductor, is going to want to pull electrons out of the negative end of the battery and along the wire. And as it flows through the wire, it's going to be able to light the bulbs that are in the way of connected to the wire, and it is returning back to the positive end of the battery. We also have the diagram version of this series circuit. So I have my battery here, and my energy flows out of the negative end of my battery, and it shows on my circuit diagram that I have a switch in place. And some of you asked last week, why do I have a switch on my diagram? So again, the switch connects the circuit to allow the lights to receive the energy and turn on, but it doesn't appear that I have a switch in this picture. Well, in order to make a switch in this picture, what I would do is I'm going to take a look at this first connection between my wire and my bulb. Right now it is connected, they are attached, and the light is illuminated. But if I were to remove that wire from the first bulb, that is the same as building in a switch. I have broken the connection on my circuit, and then since it's a series circuit, one path for current to take, there would be no path for electrical energy to move into the bulbs, and the bulbs would not light. So this is the same design as our series symbol design. I have current flowing through the switch, through the bulbs, and back to the battery. Okay, so we have a handle on the series circuit, but a lot of things that are in our appliances, in our homes, and our handheld devices, they are not wired on a series path. Because if at any point something on this series circuit were to be disconnected or broken, current is unable to flow through the rest of the circuit and nothing will be able to work. So that's the same idea as if you had one light bulb that was broken in your house and then nothing else in your house would be able to run because of that one broken section in the circuit. It just doesn't seem to make practical sense. So here is what most of our wiring is built upon. This is something called a parallel circuit. A parallel circuit means that we have multiple paths for the current to flow along the wire to reach different devices that are connected along that circuit. And parallel simply means that our wires, our circuit path, are run parallel beside each other. So in this picture here, I still have the same ingredients, the same elements that I had on my series circuit. I have my battery and I have my 3 bulbs. But now if I take a look at the diagram version of this, which is the same as the picture, I'm just using my symbols, I have a way for current to reach each bulb all at the same time. Or I could have a way for current to reach each bulb independently of the others, meaning I could turn on just the center bulb if I wanted to, leaving the other 2 bulbs dark, or I could turn on the outside bulb or any combination of this that I wanted, because current has different paths in order to get to different bulbs and back to the battery. So if something is turned off or broken in a parallel circuit, that is going to still allow current to find other routes to get to objects that are still functioning. So let's compare these two side by side before we do a little work on this parallel circuit idea. So side by side, I have the same elements in each circuit. I have my battery and I have 3 bulbs and I have my connective wires. But in my series circuit, which is on the right, there is only one path for current to flow. And at any point, if current is broken, none of the bulbs will be able to receive that electrical energy. On the left is my parallel circuit. It's the same ingredients as in the series circuit, but if I turn off any one of these bulbs, current will still be able to reach the others. So let's zoom in on this diagram of the parallel circuit. So let me go ahead and get my marker up and running here. Get my pen. Okay, so once again, it's important that we are going to go ahead and mark the negative and the positive end of the battery, because our current, our electrical energy, is going to flow out of the negative end of the battery and along my circuit path. That A that I just passed, that's an ammeter. That's meant to measure the different levels of current going through here, so that's okay. But what we have now that current is starting to flow down this path is we have a choice. Current can choose to take this first road, this first circuit path coming up, and if we just left this circuit as is, current would be able to flow down this route, light the light bulb, and continue back on its path to the positive end of the battery. No problems. Current can also choose to continue down the main road, that main circuit line, and it has the opportunity to get to the second or even to the third bulb. These could light, and in each case, current could make its return path down to that main circuit line and back to the positive end of the battery. Okay, now let's say that I didn't want all lights to be illuminated at the same time. This is where my switch is going to come in handy. So again, I'm going to mark where my negative and positive end, there we go, on my battery are. And as soon as I hook that battery up to my connective wire, current is going to start to flow out of the negative end of the battery, and now it has a choice on which direction it can travel. Let's say, though, I'm going to build in some switches here. Adding these in along my circuit line. Now, on this first route, this switch is open. It is disconnected. There's an air gap between the two lines, which means current could try to go this way, but current can't jump the open switch and connect into the bulb. So that bulb would not light. Now, current would continue along the circuit path line, and if I just wanted to light my center bulb, what I'm going to do is I am going to close this switch. And when I close that switch, I am connecting the wires in my circuit. Electrical energy will be able to flow through the closed switch, through the bulb, illuminating the bulb, and it will continue back around the main circuit line and back into the positive end of my battery. If I left my switch open on my final bulb, current would go, current would try it, but current cannot pass into the bulb to light the bulb. So this is a beauty of a parallel circuit. I can choose, using switches and using these parallel circuit lines, to light or leave alone different bulbs, fans, appliances that I have in my home plugged into the circuit. But it's only because each bulb has its own path running parallel between my main circuit line that I am able to do that. We see a common mistake. Let me go ahead and hit the eraser here. And we're going to erase all. There we go. That's better. Back to my pen. We see a common mistake where people try to put, I'm going to change my ammeter here, and I'm going to change that to a light. People try to wire something onto this main circuit line. If I do that, will I be able to turn on or off that light as I choose or as I need to? If it's on this main circuit line and I wanted to turn it off, a lot of people try this. They say, oh, cool, no big deal. I'm going to add a switch right here. That way I can turn that light on. However, if I put a switch and a light on this main circuit line, that will control everything else in the parallel circuit. That switch is going to be the judge if anything else gets current or not. So I want to avoid putting a switch on the main line that is so very close to my battery. This is again one of the beautiful things about having a parallel circuit. Each independent line for bulb and switch is what I'm going to need in order to operate each element independently of the next. So in a parallel circuit, if something is broken or turned off, others can still operate successfully. Okay. All right. So here's your practice with parallel circuits. This is the same idea as when we designed our series circuits using this animation technology on the Clio website. So you are once again going to use the link for Clio to get into that digital build of circuits. You have a new requirement in order to build a parallel circuit. And this looks really similar to the example that we just went over together. So you can build your circuit in Clio, and again, take a screenshot and copy and paste your design into this box here, and then tackle our final question. Why would a parallel circuit be more effective for wiring than a series circuit? Or if you are someone who had a little trouble opening up or running the Flash program on your computer that uses this website, or that this website uses, you can open up a Google Draw and physically draw the design of your parallel circuit that you would have done on the website and copy and paste that drawing into this box here. Please remember to follow your list of requirements for what needs to be included in your parallel circuit and have a little fun with it. All right, I'll see you guys soon.